All right, guys, we're just going to keep it simple today. And I know that sometimes parameterizing a cylinder can be difficult. So I decided I would do a video on simply just parameterizing a cylinder for like a few different cases. Um, this can be very difficult to do if you're doing surface integrals or if you're doing flux integrals and you need to do 3 surface area flux integrals. So instead of using the divergence theorem, they're asking you to justify it. Well, I came up with a nice little algorithm here, and I'm going to be doing a series of videos. It's just going to be the parameterizations here and where you might come across them. And then later on, I'll be doing a surface area integration and then a flux integration, and then I will be doing divergence. But just strictly in terms of parameterizing something, in this case a cylinder, I'm going to kind of explain this without doing Riemann sums in a way where we can use common sense to know what's varying and what we need to put into our expression. So, having said that, if I'm parameterizing the lateral surface of the cylinder, right, then what I'm going to hold constant here, and this is the most important thing, is my radii. My radius is going to be held constant. The radius is fixed in this example for this circle at r squared equals 4, or x squared plus c squared equals 4. Our radius is 2, and it is in fact fixed because I'm focused on the lateral, right? I'm not focused on anything else. I'm not focused on a slice. So my parameterization needs to be more conveniently, I'm just using x is equal to 2 cosine t, y equals y for the variation here, because y is not fixed, it can vary. If it was fixed, I'd put a number, and I'll get to that in my other example. Here z is equal to 2 sine t, and the pieces that are going to vary quite simply are going to be your y and your t. The radius is fixed, so we just put 2 cosine t. Notice how we're putting 2, we're not putting r. Y is equal to y, it can vary, and you've got your 2 sine t. Now, if you needed to do a normal vector on this, you would be concerned with r sub y and r sub t. I'll do that in another video. Now, on this example over here, I'm letting y I'm allowing y to be fixed, right? So what's varying here, and I'll get to the point, is r and t, right? So r in this case can vary, unlike the other one, where it was fixed at 2. And y in this case is fixed, and t is allowed to change as well. So your variation is in r and in t for the vector r. Not to be confused with the radius, right? This is a vector r notation. So I've got that is equal to r cosine t. That's x is equal to r cosine t, y is equal to 0 and fixed, and z is equal to r sine t. And this will basically give me the parameterization of the circle here, right? Pretty easy. So if I wanted to put this in terms of two-dimensional vectors, I sure as heck could. I could say, okay, in 2D, I've got nothing more but r is equal to, well, I am specifying here that y is equal to 0 and fixed, but you would have what would you have here, right? You would have a z and x-axis, right? And that z and x-axis would be in its own plane now if y is equal to 0. And you could literally just, what you could do is you could just put this as really you can just change your variables and do it as x and y if you wanted to. But don't get that confused, right? We're still talking about a cylinder, so I won't touch on that. But I think you can see what I mean. You would have a circle in z and x. Now, on the next one, we've got x is equal to r cosine t. We got y is equal to t and fixed. The same scenario, only a different value. I know that y'all deal with this with flux integrals when you have to do your caps, right? You'll have a cap here, like say at 0. You'll have a cap here, say at y equals 2. So for the y equals 2 version, well, it's still fixed. Nothing's varying. R can vary for both components, and t can vary for both components. So x equals r cosine t, z equals r sine t, and your r sub t, not to be confused with the radius, once more, is equal to r cosine t, comma 2, comma r sine t, where 2 is fixed. R and t can vary. Now, if I allowed r to just equal 1, right, and didn't want to vary it, and I wanted to do something, if I already knew that it was just 1, well, there would be no need to include it, and I would say r of t is cosine t, 2 sine t, and that would be a circle of radius 1 centered at y equals 2. And you would have, well, I should say centered at 0, but it would be on the slice y equals 2, right? So this tells the person that you actually have this slice up here. You've got the slice at y equals 2. That's where your circle is being parameterized. It maps out every little point along the height y equals 2 on this line, and so on and so forth. And if you allow r to vary, well, that's why I have that in there, because now you can do your area integrals. But more specifically, for any value of r, you can get the outline of where you're at here for your three-dimensional component as well as r of t. That would also be for this one, like I mentioned earlier. If we let r equals 1, you would just have the circle being parameterized here instead of the parameterization taking the path along here on this line. That's if I allowed r to be fixed, right? So I hope this helps, and in my next video I will do the normal vectors for these, and then in the video after that I will actually do their surface area integration, and then I will also do a flux integral for this. Hope this helps. Have a good day.